give him a warm welcome.
Hi everybody, here and online. My name is Oz. I'm representing Laconic, which is just my one-man AI advisory. Nothing very interesting there. But first of all, big thanks to Softlandia team, especially to Mikko, Henkka, and Ilmo. Great event, great facilitation. Thanks for the invite. And today I'll be talking about developing machine learning solutions in an efficient manner. Of course, we care about efficient machine learning solutions, whatever that means, but it also makes sense the development process is efficient, so we leverage basically the whole thing. My background is machine learning, been leading machine learning team in a machine learning consultancy, about 20 people team before, and nowadays I'm running my own thing. All right, so quickly I'll be talking about these three topics. I'll go a bit almost philosophical at some points, but there will be some practical examples as well. So I'll take this word efficiency in a holistic way. So not necessarily some kind of a numerical quantifiable thing always, but I will basically emphasize that it's not a one-dimensional concept and it has trade-offs. And secondly, I will talk about this in various levels of abstraction in our machine learning development process, from all the way to low level to high level, let's say things like communication and information sharing, and then what does it mean in the value chain when we create solutions with machine learning. So I will start with the very common, but somehow I believe wrong model of looking at efficiency, and it is this. Many people talk about if we use this kind of processes, this kind of tools, this kind of algorithms, or this kind of infrastructure, we will be more efficient. And if you don't do that, we will be less efficient. I think this is way too reductionist to an extent that it's misleading, if not wrong, I would say. Because how do we know that? Because simply in real life, if it would be that easy to apply these tools and be more efficient, we would have done it. I think as humans, we have pretty good innate understanding what is efficient. Somehow it's embedded in evolutionarily. We want to save energy, and we know what the concept of doing things efficiently, right? So let's say there'll be pizza coming, and there will be several pizzas. Probably they're not baked at the same time. The oven is not that big. So somebody's baking them, but one person will be delivering all of them once, because that's the efficient way. You don't need to teach them that. It's just very normal, right? Or if my shirt gets dirty, I wait for some other clothes to get dirty to start the machine. Who starts the washing machine just for one shirt? Because that's just very normal, and I don't need consultants from Boston Consulting Group or something of that sort, or Gartner to teach me that. So I don't believe we don't know what efficiency is, but it's more of like this, that it's a landscape and it's a multidimensional concept instead of unidimensional. We are efficient or not. So we have, of course, efficiency in terms of developing the machine learning solutions. We have efficiency regarding data. Data collection can be more efficient. Data annotation, which is a separate thing, can be more efficient or less. We have all kinds of other metrics. These are just examples I wrote. So efficiently maintaining a machine learning solution, deploying it. Of course, the lower level stuff like computation efficiency and things of that sort. So I believe it's more effective to look at it in this kind of holistic view rather than we are efficient or not. And the bummer thing is that typically these metrics, or let's say efficiency dimensions, they have a trade-off with each other. It's just how it is. And data scientists are very familiar with trade-offs. There are all kinds of trade-offs in data science, machine learning, like bias variance trade-off, precision recall, specificity, sensitivity. They are in trade-off with each other. In computer vision or in other fields, larger models are typically slower. They perform better, but there's all kinds of trade-offs. And what we look at is in this kind of Pareto optimal. We are searching for this Pareto optimal or some sort of optimal for our context efficiency. And just like a neural network, in some sense, we are probably operating on a local minima that this is good enough with these different efficient metrics, and it takes energy to jump to explore some other efficiency metrics or efficiency dimensions. So I believe this is important when I start my examples to take this holistic view into account. And I can start with this levels of abstraction in machine learning and developing machine learning solutions. Low level abstraction is stuff like really our computer science stuff, like space efficient, memory efficient, and compute efficient algorithms, latency. And mid-level things are more like MLOps stuff. So how do we deploy these things, version, containerize our software stack? Do we use PyTorch or TensorFlow or whatever? And high-level concept is stuff like, how do we communicate in the team? Obviously, we are working in teams, right? How do we communicate with each other? How do we represent our results, present our results? How do we ask the question? Really super simple things, but very important to have that also efficient so that other things are leveraged. And let's start with lower level concepts. I couldn't come up with the, let's say, simplest algorithm, median, like calculating the median. How do we calculate it? We just calculate it with NumPy or Pandas or whatever, or pure Python, right? But let's say if you have a lot of data coming in a stream way and you want to calculate median all the time, well, median is not very efficient to calculate because you need to sort, right? Like median by definition requires you sort your whole array. So can we do something more efficiently? Well, you can use this divide and conquer method. You can just chunk your data and calculate median of that each chunk and take the median of those medians, which is way more speed efficient, but it's slightly not exact, so it's approximate, but it's a very efficient way of doing things. Or we can use mean, right? So we know from probability theory that basically any probability distribution, the difference between the mean and the median is at most one standard deviation. So if we calculate our standard deviation, which is fast to calculate, and if it's small enough, we can just use mean instead of median. It's a good enough approximation. So you can see already the, let's say, trade-offs between having an exact solution but slow, or somehow close enough solution but really fast. And this is really low level stuff of developing machine learning algorithms. And let's say the second example from neural networks, something called importance sampling. I don't know, and curriculum learning. I don't know if you're familiar with that. So importance sampling is a very intuitive concept that in our data set, training data, not all training samples are equally informative. This is almost always like this, meaning that some training samples are really easy, and we don't need to show that to the model over and over again. So we should actually sample difficult cases more because they are more informative. This is not typically done, but we should do it. And curriculum learning is that there are lots of empirical evidence that showing easy samples to the model first helps, and then getting the task harder and harder, just like how a basically human child is learning. And typically, if you employ these two solutions, you will reach an accuracy much faster. So you are more data efficient, actually. You are more compute efficient. So you don't need to pay a lot of GPU compute on AWS. If you run these like fairly simple things which can be implemented in couple of lines of code. But these are low-level stuff. Maybe another example is retrieval. It's a well-known problem, and I'm sure every data scientist will face this problem. It's basically how can we find similar objects in a database. For example, finding similar image. You have an image and you want to find similar image in a database or text. Basically, every search engine is retrieval. You are writing something to Google and it tries to find similar text, or product, or Spotify when you search a song, it retrieves, or whatever. Every recommendation engine is some kind of retrieval of sorts. And let's say the first way, the naive way of doing things is I have a query. This is a representation of our object. It can be an image or a text. These are basically our features, numerical values, and I have a database of those numerical values, and I want to find the similar ones, right? And of course, I can just calculate the distance, basically high school geometry, Euclidean distance, or whatever, and just go through all my database, right? And just pick the closest ones. Well, that's pretty stupid because this does not scale. Like, if you have 1 billion images or 1 billion entries in my database, I don't want to calculate these distance 1 billion times every time somebody searches. So when I search something in Google, of course, they're not calculating all the website, all the sentences in the world at that very moment. They do something smarter, right? They do indexing. So what is indexing? It's a fancy way of saying pre-computed lookup table. So you have your data. This is your numerical representation, and you save it in a database. What you do is you pre-calculate these distances in a smart way. I'm not going into detail. You can build your whole career only in this topic. You just save those pre-calculated distances in a lookup table, database, whatever you call it. We call it index. And once you have it, when a new data comes that you want to search, you just start, okay, let's compare in my database the first entry. You spend 1 compute cost of calculating the distance, but you know already this entry is far away because you can, in a very fast manner, look up from a lookup table. So you don't need to compare all these that cluster, because you know that will be far away. I don't need to search that space. And you do it a couple of times, and very efficiently, you can actually decrease your search space into very narrow one, and then you can just brute force your way around this point, find the similar images or whatever. And this is a very low-level concept of machine learning solutions, but there's quite a lot of, let's say, libraries somebody implemented, right? There's Annoy from Spotify. I like it quite a lot, open source. NMSlib, pretty nice. Files from Facebook. Scan is rather recent from Google. So these are Python libraries that you can just build an index and it scales to billion images, billion entries, whatever that is. And you don't need to implement this thing, and you don't need to care about the hyperparameters of that much. So my point here is that for low-level concepts and tasks, things are pretty efficient and somehow abstracted already. I mean, Python, we mostly use Python. It's already a very high-level language. Nobody writes in Fortran or something. So everything we do is already quite efficient. And my experience is that you shouldn't spend too much time on this, like making this part efficient. And I will explain why. And because it's already pretty efficient, these low-level tasks. Let's go to mid-level concepts, so a bit higher up. And this is more of like how to deploy things efficiently, right? And I will continue from the same example. Let's say I have this, I use one of these algorithms that I can index, which is again, fancy way of pre-compute distances and save it. But how would I deploy that, or which one to choose? For example, if my data is sparse means with a lot of zeros, NMSlib is pretty good. And if I'm deploying, let's say, with Google Cloud CPUs, with AVX2 support, which is nowadays pretty standard, scanner really works well. So I should use that. But this mid-level concept is basically focusing on where to deploy, how often should I re-index when new data comes, how often should I run this re-indexing, and these kind of questions, how should I load balance suddenly if lots of people search? And focusing on efficiency of this part, it gives you a bit higher leverage than focusing on, let's say, lower level, how to compute medium more efficiently, in my experience. There are, of course, exceptions. If you do it properly, scan here is accuracy, we call it recall, and this is queries per speed, let's say, and top right where we want to go. And scan from Google is, if you do it properly, these two parts, deploying it and AVX2 supported CPU, it's very fast, very accurate. And these are all the other methods. So this is the benchmark. You don't need to do it. And again, this part focuses on lots of tools like MLOps tools. And I'm not going to say this one is better than that because there are way too many. And I also don't think it's a very strict case that, let's say, Metaflow is way better than MLflow or vice versa. You should probably use these tools because they are needed. There's a reason why they are there, but I wouldn't spend half a year trying all of these out. Just pick one and focus on the efficiency. I would definitely use DVC, data version control. We all use code version, of course, but versioning your data is important. Probably I would use Metaflow or MLflow of some sort to operate and orchestrate my experiments. And it's good to have some sort of flow diagram that fits optimally for your organization and for your team. This is just one example. I can share the slides if you want, so you don't need to follow what Google does, because that's not optimal for you most likely. And let's come to one level up, so higher level concepts. Efficiency of, we started from really algorithmic low level stuff to mid level, and high level concept is, I believe if you make this high level concepts more efficient, so how to develop a team for machine learning solutions, for example, I believe you have more leverage actually when making the whole thing more efficient, because it just trickles down. You can think of it that way. The efficiency in running projects or solutions trickles down to all the way to mid and low level. And let's continue from the same example that for low level of this vector search retrieval, you are talking about really some kind of parameters of some algorithm, and you can tune them to an extent that it's really working well. That you save some efficiency, fair enough. But for mid-level, I think you save more efficiency, or you get more efficiency in several regards, several efficiency metrics. If you focus on where to deploy, when to reindex, how to save cost in cloud computing, and how to monitor usage. Is everything down? Is everything even working? So that's probably focusing on that part of things and doing that more scalably gives you better bang for your buck, if you call it, than optimizing some hyperparameter of one of these algorithms. But then there's another higher level, let's say, opportunity that, how do I know these things exist? I sure don't want to implement this alone or from scratch. So knowing that this problem can be solved with approximate nearest neighbor, or this retrieval or vector search, different names, that's a huge leverage. Somebody in your team, if somebody knows that and hasn't shared this info, that's pretty bad, I would say, because you lose so much time searching that, oh, this thing exists, or even worse, trying to implement it yourself. So optimizing the communication, in this case, that's like a huge leverage to everything else. So I believe that soft part is even more important than, let's say, optimizing some super low level stuff, which might be sometimes needed, of course. And a couple of tips I have in my career used is fake product release. Have you heard about that? You don't release it to the public, but especially as, let's say, problem owners or machine learning leads, you have a problem and you haven't even written a single line of code, but you write a 1.5 page product release as if you have developed this and it works. And it's a mental, let's say, focus mindset that what do I want in this product that I'm developing, this machine learning product or machine learning feature of a product. And then it gives you super nice clarity. It's not easy to write this thing down, actually. How would I want this to be released if I do it properly? Like, this is your optimal scenario where things went really well and it works. How would I write this product release? And this you can use as a guideline for yourself when leading the team, or even share with the team. This is not actual product release. This is for before starting the project. And regular retrospective workshops internally, like when you're developing machine learning algorithms, it doesn't make sense every 1 year. It's too, let's say, scarce to have, hey, how are we doing as a team every 1 year? Do it more often. What can we do better? What can we improve in our process of collaborating and coding? And knowledge sharing after each milestone. Let's say we finished one phase of developing an algorithm, or we released the first phase, or if we are a consultancy, let's say we finished one project, and the people who were involved in that should actually explain quite in detail how that went to everyone else, so that knowledge is shared. That creates a huge leverage for the whole organization and for individuals. And sometimes it's even, as I would say, equally as important to have this soft guidelines of software development than like some hard guidelines. We should definitely have some, let's say, software development guidelines, how to write good code. But soft guidelines is stuff like how to ask a question, really. Let's say you are in an organization, there are senior developers, senior engineers. What would be optimal way to ask a question? Damn. So that I can waste little amount of my time and their time. Typically, the biggest mistake I've seen in juniors is that they don't explain the problem, but they ask about a question regarding what they have tried. So they don't put the context to the senior. Hey, this is my problem, and I did this, and this is what I'm facing. Instead, they ask, hey, this is what I'm facing. They don't explain the problem that they're trying to solve. So I think as seniors and leaders, it would help to give really these soft guidelines, how to communicate, how to ask questions, how to share info. If something is blocking, how to basically get rid of that as quick as possible and being proactive about that. This creates more leverage in the long run in developing machine learning algorithms. So this was my talk. I am on time. Thank you very much. And I'll be happy to answer some questions if I can.
Yes, thanks a lot. Very nice talk. We have time for questions, so who wants to go first? While you're okay, awesome.
Thanks. That was very interesting. I'd like to ask about your opinion about the future of developing machine learning solutions efficiently. Like, we have the price of computation power is going down. Auto ML is coming up. We should get kind of like trends that rather make us care less about being efficient and about the details you just brought up here. So how do you see the future? Should we even care about the efficiency, or should we just leave all that to auto ML to care about?
Thanks, Mika. Very good question. I think, in my opinion, most of those tools, they are able to improve efficiency when that efficiency metric is quantifiable. Well, for example, AutoML, because that's quantifiable, some accuracy or whatever. Then you can automate quite a lot of part of that. So it maybe, I would say that part fits more on the lower abstraction level of tasks and concepts. And I can pretty confidently say that let's say those tools or the development evolution of the field is abstracting more and more all the time. So back then you had to write everything in maybe C, and now we have Python and we have libraries, and now we have even AutoML. So things are more and more things are getting abstracted, but coming from the lower level to higher level. So in my view, it still holds that this higher level, focusing on the higher level efficiency, still trickles down. But I agree that, which is a good thing, that many lower level concepts are getting already efficient, as I mentioned, and more will follow the same pace, I would say.
Makes sense.
Small question about you were telling about like how important the soft things here, especially you were talking from the point of view of development of the solutions. I was thinking, like, do you have any tips for the soft skills, or how you would approach a customer which wants to identify like what kind of problems that they have, maybe solvable with the methods that we use here?
Yeah, I have a couple of. So what I've worked in my experience is let the client just list down all the use cases, even wild ones, without letting them care if it's even science fiction or not. Just, hey, we are a large organization. Let's list down our possible ideas or opportunity points that we can utilize machine learning. Like, really be open-minded there, or let the client be open-minded, and then show to the client that how you prioritize those use cases. Okay, these are the low-hanging fruits in various metrics. Let's say development, ease of development, or ease of deployment, or how realistic the data is ready. Like, you can do that kind of workshop. It doesn't require a lot of space, but then they see how you think, how you assess this use case is more suitable for machine learning than the other, which gives them confidence that, okay, these guys are not just coming in and, hey, should we start developing this use case for you? Like, why? So you build the background why you ended up proposing that one. That actually, in my experience, worked pretty well. So this is a bit soft skills towards the customer, as you said, rather than internal. Yeah.
Like,
Thanks. Just raise your hand if you want the microphone. Okay.
Hiya. Thanks for the talk. I just wanted to ask you what's your opinion on Agile and Scrum, because that sounds very high level, optimizing of that high level thing.
Yeah, I like it, but I'm not hardcore, like, die-hard fan. I give some leeway. I have seen people successfully develop machine learning solutions without using Agile framework. It's clearly suits better for, let's say, traditional software development, various reasons.
Could you give a reason?
Yeah, because there's more uncertainty in machine learning projects, uncertainty in several regards. Again, it's in several meanings. One is it's rather new field. Even there's a lot of buzz. You have to understand it's still very new field for lots of industries, especially old school ones. It's like something they hear on LinkedIn or something, but it's nothing concrete. So uncertainty in the problem owner part and buyer part, and estimation uncertainty of of a, let's say, development process. Probably we are getting more certain. We know more about, yeah, we use these algorithms. Things are getting more abstracted, and we have tighter estimates of how long it will take. Let's say human hours and calendar days. And I think the uncertainty regarding of course, the performance is just there. So I would say this uncertainty makes it a bit more difficult compared to, let's say, more traditional software development projects. I'm talking about the agile context. But I have seen it work like with or without agile. I use it sometimes, mostly because if the client requires that, I'm not like a diehard fan. Yeah.
Right. Thanks.
Oh, hello. Thanks for the excellent talk, Jyrki from Visu. You have some comments about like a deployment on the like a long run. If you think of a solution that we hope that will actually be there for hundreds of clients for, let's say, 5 years, 10 years. So, what kind of comments do you have on that? Since I know the field is evolving.
Yeah, I would say the current best practice is you should never deploy anything manually at that scale, meaning that you should have continuous integration, continuous development, some pipeline, some checks, unit tests, whatever, rather than calling your senior engineer, hey, can you deploy now, when you come to at that scale. So that is, I would say, pretty well-known practice for that sort of stuff. What tools to use, then I don't think this is the way to go. And I'm more on the data science part rather than engineering part also. That's not my hardcore expertise anyway, but definitely something more automated for that scale, it has to be done. And secondly, nowadays, also this concept drift or data drift, where statistical proper use of the data shifts for various reasons. There's COVID or whatever, something happened. And monitoring that, I think, is even more important for that kind of long-term deployment processes. So you have certain alarms and checks, and there are solutions in, I think, I would say all large platforms, Google, AWS, they provide that sort of services to monitor these kind of things.
Yeah, thanks.
Thank you. Okay, time is running, so Oz will be here, right? You will be here around for some time if people want to ask questions. Thanks again. So next, we welcome Esin Guldogan on stage. She's done her PhD here in Tampere and worked at least Nokia, Huawei, now Microsoft. So great to see what you will show us tonight. I'll set your slides just a moment.
Thank you. Thank you very much for the previous talk to Oz. It was very informative, and I specifically like the fake product release idea. Very impressed. Yeah, okay.
Great. You can test the clicker if you like.
Yeah. Okay. Good. Hello, also from my behalf. Nice to see very familiar faces and also new faces. And also thank you also from my behalf to Softlandia for this opportunity. First time I'm combining my ambassador thing for imaging in Tampere and also Tampere AI ecosystem. So now it's all combined that I do this presentation. I'm very happy. So today's talk will be about very high level. I won't go much into details, but of course, if you have any questions, we can go deep dive. I'll talk about how we use AI in mobile imaging, or what is the generic use case for mobile imaging, and then also maybe the future. So here we will talk about when we say data, it's visual data. So it will be images and videos. So what Oz was mainly talking about all types of data, but this is more like fun part. So of course I'd have to start this whole talk with this very iconic image that probably, of course, we all know how mobile cameras became a part of our life, that we don't use DSLR cameras anymore because we have our phones with us. So we capture images even actually beyond the DSLR cameras currently. With last couple of years, they have been capturing unbelievable image qualities that you all know. And it became part of our life. And then they also improved the quality, but then they also introduced these new use cases. So we don't only capture images or videos, but we do a lot more with the mobile cameras nowadays. That we will probably talk later. So these are the main differences, physical differences between the DSLR cameras that we have been using and then mobile phone cameras. So lots of cons actually from the mobile camera, from the physical perspective, because you can't really beat the physics or the image quality. The more the photons you have hitting the sensor, you have better image quality. That's the end. So you can't really beat the physics with this. You have larger space, then you have more photons. That's it. So that if you have larger aperture size, you have more opening, you have larger sensors, you have more photons, hence you have better quality. But what if you don't have? So when you don't have this much bigger sensor, when you don't have big aperture, then you have limited zoom capability, what you can do. So there, then how you fill this gap is the high computing power, meaning nowadays is basically the AI. So AI in mobile imaging is actually is trying to fill this physical gap between these two cameras. And along with this, it also brings new use cases because it can also improve beyond the image capability. So, of course, because I will be talking about image quality and ISP pipeline and imaging algorithms, so very basics. So from the sensors till the JPEG image that you are saving or seeing currently, that along the way, there are multiple algorithms. So some of them reduce the noise, some of them filters, some distortions, and some of them improves the color, some of them makes the white balance better, not so dark, but brightness is slightly better, for example. So these are very high level. But like more or less, most of the basic ISP pipeline having these algorithms, most of them know. But then, as we talk about these two differences between the DSLR camera, or like let's say the ultimate goal which the camera can have, but then mobile cameras cannot have because of the size, and because of the cost, because of the inefficiency in the mass production. So because you can't really put large sensors, or maybe you can put large sensors, but then you can't really integrate it there, or maybe you integrate it, but you can't really mass product it in that way. So there are multiple reasons beyond that. So while you can't do that, then you have to fill this gap. And what are those limitations? Basically, I try to categorize them to this, like sensor size and limited aperture. Then you have more noise, more distortions in the image. And then you have this limited dynamic range, because then you can't really capture all the information because of the limitations. And then you have limited depth of field that would create to like your focus distance and focal distance, and then you have limited zoom capability. So I'll give simple examples for all of this. So it's all started actually with the traditional algorithm. So this gap has been always there since the mobile cameras started, like with Nokia, and then, as we all know, then we try to fill this gap with the traditional algorithms. So this mosaicing and denoising is the very first algorithm that from the sensor, if you want to make some visual image, that's the first step that you need to do, the mosaicing. And then it was all started with the traditional algorithms, but nowadays, most of the mobile phones that we are currently using, they have AI-based mosaicing and denoising. It's because, well, AI algorithms are outperforming the traditional algorithms simply because they are non-linear. Then the next thing that we are trying to fill the gap with an AI is the HDR. Again, most of the current mobile phones that we are using, they have AI vision or AI HDR. Basically, you are fusing multiple exposure information with an AI algorithm. This is an example from Apple. They call it deep vision. So they have like exposure stacks, regular exposure or short exposure, or they also have long exposure. So with the traditional algorithms, they are stacking the same exposure frames, and then the last 3 frames are actually fused by AI. So then AI does local optimization. So it's not only fusing linearly all 3 pixels coming from the 3 different frames, but it actually applies localized processing. So that's the beauty comes from the AI vision. So that's why, although we have nowadays HDR sensors, but AI vision is still used even with the HDR sensors because it brings more information than the basic HDR. So it's beyond the HDR because it gives the highlights, it gives the details and shadows much better. Again, speaking about the low light and long exposure. So AI power again comes especially in the low light cases. So low light is the most tricky condition in AI, in mobile imaging, because it brings noise. You have the less image or less photons that you actually don't have specific information that you have to recover. And so you don't have the details, you don't have the light there. So there are multiple things that you need to recover in the image. And then this is where the AI plays a big role. I think this is where it's the biggest gap between the traditional algorithms and the current ones is for example, Google's night sight, or deep vision is also having a low light version of it. This is where the kind of beauty of the AI is clearly visible, that you can create actually very, very good night images. So. Then again, talking about this lenses, but now when we have this small focal length and fixed aperture, then we can't really have this natural bokeh like the DSLR cameras that has. So since you don't have it, but you can actually fake it. So this is how all the cameras are doing. That it's the bokeh applications currently in the mobile phones are the fake ones, because none of the mobile cameras can have that much like big aperture and then create that much natural blur. So what you do is actually there are plenty of process behind this. So first of all, you need to create a segmentation algorithm that you strip out the foreground person from the background, and then for the background also then the foreground object, you need to have a depth map. So basically you need to have, for every pixel, you need to know where that pixel is. So you need to know the distance from camera to the objects. Then you can apply realistic blur, because blur efficiency, or like the blur strength is actually increasing with the depth. Same with the DSLR. So the further the object is, the more blur, but then the closest objects are sharp. So that's what you apply. Then you have to have the depth map for the portion. And then there were plenty of other things on the whole pipeline that you can do with an AI. AWB is like white balance, auto white balance. You can do deblurring, meaning that you have a long exposure, and then there has been a moving object on the scene, and then you have a blur image. Then you can apply AI deblurring, which can combine maybe multiple frames or not. Maybe simple estimation that it just creates the blurring. Ghost removal, like again the same. So if you have fusing multiple frames, and then you have you couldn't fuse it because it has been moving during the photo capture, then it created ghosting artifacts. Then you can actually remove those with an AI. Sharpening is also one way. It's kind of a like enhancement that it sharpens the textures and edges in the image. There are even algorithms with an AI currently that is replacing the very fundamental, well-known traditional algorithms like compression. Compression has been there, God knows how many years. It has been a research, but then it is nowadays like even outperforming the basic fundamental algorithms, which has been a long time research topic. And then, of course, there are even also solutions. They are trying to replace whole end-to-end ISP pipeline, meaning that they want to have input from the sensor, and then they want to output compressed image, whole pipeline. Of course, there are, well, challenges on that, but there are at least studies and activities trying to replace the whole thing. Not an easy task, but there are attempts, let's say. And then I'll go a little bit more high level. So now we are, let's say we talked about the ISP, so that we try to improve the image quality, and then we try to beat the physics, and we try to replace the traditional algorithms. All done, we have good image quality images. But then what else we can do within AI? So we have now good quality images or videos, but then we have lots of information actually that we use during this processes. And I call them like intermediate outputs, but they can be enablers. Well, we talked about the depth maps, but depth map is also one enabler. It's an intermediate output that you used for bokeh, but you can actually utilize it for many other things. So you have that intermediate information. Similarly, you have semantic segmentation. So you segmented out foreground and background objects, but you have now that information. You now understand it, that image is including a person, image has a building, image has a sky. So what do you do with this? Again, you can improve the image quality, but you can also create applications with these informations, like, again, like detections or trackings or optical flows and whatnot. So there are so many other. And how this whole thing is like, now this image object detection and image computer vision algorithms, and it became a big community and big ecosystem. Now it all started many years ago with an ImageNet. It's basically very, very large scale image data set. And every year there is a challenge, or let's say competition, between the companies or the research groups or the academy, then who is doing the fastest and most efficient and most accurate classification or segmentation or object detection. So challenges can be many, but this became a big ecosystem now that it brings and it serves the community so that the research is always ongoing to improve things in many ways. So it never stops. So this challenge specifically is the most important one, because it brings this kind of very large scale networks, so that they need to be efficient, fast, accurate. And these networks are specifically placed so big role because these pre-trained networks are also used as a backbone for the many other small ones. So if you are doing any computer vision AI models, almost 99% cases you use one of these backbones, pre-trained models. And this graphic changes almost like monthly. So when I give this talk, this AI and mobile imaging, in many cases, each time I'm also surprised even myself, like if after 6 months, this graphic changes completely. One type of new group comes and they create a new efficient network model, and then it changes the whole thing. So it became a game changer until the next one. Then it became a game changer. Like this efficientness nowadays, that it is the new game changer, but I'm sure it will survive 1 year, and then there will be a new game changer. So the efficient net comes from the Google Brain team. It's basically a transformer model, but currently it's the most efficient one, with both from the number of parameter, low number of parameter, high accuracy. This is also one way to, these kind of graphs are also very useful for the researchers and also for the developers to understand the very basic things, like the bigger the model is not always the better the accuracy. So this basically proves that. So number of parameters much more smaller compared to the other ones, but then you have the quite efficiently and accurate algorithms. So it's not only about the data, it's not only about how you train things, but algorithm is also there. So algorithms are still quite important. You can't really discard that, like, okay, this became mature enough now that we just find UNet and then get like, oh, okay, we have our data, we train it, and we will find a solution. That's not the case. You still need to do data engineering, and you still need to have algorithm person who develops the algorithm for your name. So what you need for the, again, requirements for the AI, yes, algorithm is there, but then you need data and you need parallel processing optimized hardware. Basically, you need GPU or NPU. And I've actually put here, maybe not so visible because of the conquest, but so there is a web page called AI Benchmark. Basically, it benchmarks mobile phones or laptops or like all the GPU cards currently on the shelf, that you can actually run certain models, and then you get your AI score, because it's all about like how many gigaflops, how many teraflops that you can run, so that you would know the capability of your device, of your platform, so that you can plan your model accordingly, and then you can deploy it accordingly. So, and probably we don't need to talk about the data and then black swan phenomenon. The time, do we still have time? Okay. So what is next? Of course, we shouldn't be closing this talk without talking about the diffusion models. Visual transformers are playing like quite much place in the computer vision world, and then of course generative models are coming. GANs may be used mainly for still augmentation and training, but diffusion models are also started to be used for basic computer vision tasks, like even for denoising and filtering or enhancement. Many diffusion models are coming out now. talking about meta learning, that's actually one of my favorites. I think it will become also very in the future hot topic, because we need faster AI systems. Like we need efficient ones. We need to generalize the models for more tasks, and we need to optimize the whole architecture. So as a summary, if I may, so mobile cameras are always essential for the users. Data is always important, but then custom silicon or end-to-end optimizations are also the key, because NPUs are coming quite powerfully now, but almost every sensor will have own NPU. Audio will have own NPU. Image will all have own NPU, so that everybody will have their specifically optimized hardware accelerator for their specific need models. And then what is next for the whole computer vision is actually understanding the photos, basically contextually understanding what is this photo is about, where we are, why we are taking this photo, so that it will actually fuse all the information, all the multidisciplinary information, so that it will optimize not only the image quality, but also the usage of it. That's all. Thank you.
Thanks. So a fascinating topic because you're so close to the hardware and it must play a big part. And the hardware also keeps changing quite rapidly. So I bet there's a lot of issues to solve that are quite unique to this topic. I would like to ask the first question. So how do you build the confidence that, okay, now my system is ready. I will deploy it to billions of devices. What steps do you take?
Probably it's never that ready, but kind of when this is satisfactory enough, then you deploy. There are actually objective and subjective metrics that you need to reach, and you do a lot of tests, and then you have your benchmarking system that you benchmark your results according to the previous solutions or existing solutions. So based on numerical results and also subjective tests, then if it is better, efficient, fast, cheap, or many also other things, then you deploy. But it's never ready, because then you continuously trying to improve your model, and in the next software update, you actually update your model as well. Always like that. Never ready.
So constant improvement.
Yes.
Thanks. Okay, who wants the microphone? Let's start here.
Thank you for super interesting talk. I would like to ask, typically when you deploy a machine learning model to some, let's say, cloud environment, you have a chance to redeploy it because you have new data, you retrain, or even on the device, you set up a retraining or adaptive way of learning. But if I understand correctly, this is not possible. So you deploy, especially if you are doing really low-level end-to-end thing, you deploy to billions of phones and a neural network, and that stays there. Do I understand correctly? And is there any movement towards, let's say, on-device learning of that? Maybe, let's say, HDR algorithm learns my preference or something of that sort, so some personalized way of updating the neural network models.
Yeah, thank you. This is a very interesting question. Thanks. Also, we couldn't talk about this personalization. It has been always there, but as far as I know, currently none of the mobile phones does that. So it's static. So you can only update the model if you do software update, and if the user allows and download it and installs it. But otherwise, it's static. You can't actually redeploy.
Thank you.
Next one, last question. So basically, nowadays we know that we talk about generative AI networks. So basically, what do you think about ChatGPT?
What do you think about the GPT-4 image analysis tool also compared to all the other existing algorithms?
Well, currently it's not used for computer vision problems. So it creates images that there are also, like, not for ChatGPT-4, but diffusion models that are actually used for computer vision tasks like denoising or super resolution. But ChatGPT-4 as itself, it's just generates images, so it won't be.
So it won't be able to detect which type of image, what it is, and
No, I don't
classify the images.
Yeah, yes. Currently, it doesn't have that object detection capabilities, as far as I know. It's usually text to image generation, generates image.
From the image, it cannot tell that, let's say, we have.
I haven't tried the ChatGPT-4 for that purpose. At least, like, as far as I know, it doesn't do that.
Do we have anything on the chat?
Okay, thank you. So you mentioned something about those constraints and limitations in a mobile device. So energy, computational power, memory, I guess. So could you talk about what's the bottleneck currently when you run these neural networks, large networks on a mobile device? What's currently the major bottleneck in being able to run even bigger networks there?
Yeah, thank you. That's also a very good question. Bottleneck is the memory and the computational power. And like with the NPUs, actually, they solve the thermal release issue because GPUs are actually having this thermal release issue quite much. NPUs are not that like inefficient in that side, but they still, you need memory and then the computational power from the NPU side, which are developing quite rapidly, which is a good news, but you always need more bigger ones, so never enough from memory and computational power. So that's also one of the rules.
Do you think it will be hardware or software improvements that enable these bigger, powerful models in the near future?
I always believe is end-to-end optimization. So it's never only hardware or never only software, but it always, like in every solution, it has to be end-to-end optimization. So you can always fine-tune and optimize things both from hardware and software side. I think it's end-to-end.
Now, talking about small hardware, it's always like having the battery problem and the memory. And if it comes to the battery, at least my phone is always the battery is empty. But if you think about other than mobile phones or small devices, cars, whatever industrial processes, will it be the same problems? I know the cost is problem always there, but in a way, is there something that we can do in the industry or automotive which in a way bypasses the mobile world?
Yeah, that's interesting questions. Or from the, like, if this would be from the NPU or GPU perspective, maybe power will not be issue there, or because you have a more larger space, let's say, you can put maybe larger memory also there, but still the technology and the cost will limit the computational power. So the computational power will be always a limitation. There needs to be improved all the time. I think that would be the bottleneck, at least for that case.
Thank you.
Thank you.
All right, just a reminder to ask questions in the chat. We can ask them after we've heard Zander's talk, but now it's my pleasure to welcome Zander Matheson. So he's been a data scientist and working on machine learning infrastructure at Heroku and at GitHub, and now most recently at Bytewax. So Zander, please, stage is yours.
Hey everybody, I'm going to just try and take over presenting here. So just give me 1 second.
Yep, I will close mine.
A window. Well, I can only share my whole screen. Okay, can you all see my screen and hear me? Cannot not actually tell if you can see me at this point, so please someone just let me know by speaking up.
Yeah, always good.
Okay, cool. So I'm here today to talk about real-time machine learning infrastructure. I'm Zander, and before I get going, I always like to give a little introduction on where I came from and how I ended up here today. I'm talking to you all virtually from Santa Cruz. I live in California, and I'm quite thankful for the fact that our time change happens a week or 2 weeks before your time change, so it is not as early in the morning as I expected. Anyway, I'm originally from Canada. I grew up in Vancouver. I studied as a civil engineer there and worked as a civil engineer before I went to business school in France at HEC Paris, after which I moved to the United States, where I currently reside, and I started working in speech technology, or for a speech technology company, which got me interested in machine learning. After which I worked at, as Miko said, at Heroku and then at GitHub. There I worked on problems spanning from data science, data engineering, data infrastructure, and machine learning infrastructure. And it was there I learned of the importance of machine learning infrastructure to support models running in production. I left GitHub to start Bytewax. Bytewax is a company, and there's an open source project from with the same name. It's a Python stream processing framework. It's open source and available. You can check it out on GitHub. When I'm not working on Bytewax these days, I'm often looking after my 10-month-old daughter or playing with her, and she's the cutest thing ever. Her name's Saya. And so that's a little bit about me, and now we can get on to talking about machine learning infrastructure. Today, we're going to cover 3 parts or 3 big sections in this. First, we'll get some definitions out of the way, just to kind of level set, and then we'll talk about methods supporting real-time machine learning or implementations supporting real-time machine learning and supporting architectures, and we'll kind of dive into those. The goal of this talk is just to give you an overview of the different architectures that you can use to support real-time machine learning and what is real-time machine learning and sort of stacks that support that. So what is real-time machine learning? Real-time machine learning is any implementation of machine learning where the end-to-end latency of the system is perceived to be real-time by a human. So it's generally sub-second latency. And then 2 other terms I'll just introduce because they're often heard in conjunction with this is batch and streaming. So a stream is a continuous flow of data, whereas a batch is a group or set of data. Stream processing or a stream processor is something that processes a continuous flow of data, one datum at a time, whereas batch processing, you're processing a whole batch of data. So now that we have that out of the way, we can move on to the rest of the talk. So we have that context. So in your day-to-day life today, you've most likely interacted with systems that are real-time machine learning systems, from content personalization to recommendations, fraud detection, dynamic pricing, financial markets, etc. And historically, these systems have been built and only by larger companies, and that's primarily because there was a lack of available infrastructure to support these in the past, and also to some extent the algorithms to support these were maybe not readily available or have been improved upon in recent years. Okay, so what exactly are the ML method or the ML implementations that can support real time? You probably have two categories that I'll just introduce quickly. You have online machine learning, and you have offline training with online inference. So online machine learning is as it sounds, is when everything is happening in an online sense, or sorry, online fashion. So you have your feature extraction, any other pre-processing required of the data, and you'll have your model prediction and your incremental training all happening sort of inline. Offline training and online inference is a more traditional method where you're training your model offline and then promoting it to a system that can handle making inference in real time. So in an online machine learning system is basically you have a set of algorithms that can process and update the model and make the inference one datum at a time. And this is generally unsupervised methods, so there's no human in the loop. And it's particularly well suited to dynamic environments where you have changing data distributions or something like that. In the offline-online mix, you have your historical observations, training your model. Your model is then promoted to a serving layer. And then when you have new observations, you'll have your transformation of that data as required. And then it is put somewhere where it can be retrieved by the serving layer when there's requirement for inference. Okay, so let's dive into the architectures that support these systems. So we have two architectural diagrams here. The top one is the online machine learning, and the bottom is the offline training and online inference. So in an online machine learning architecture, you generally have a streaming data source or streaming data sources. You'll have a stream processing layer, and in the stream processing layer, you'll have your data processing, and then your model is incrementally updated and the prediction is made. The prediction before the model is updated normally. And after that, your data will be output either back to the streaming platform or out to a low latency storage layer or for retrieval later on. Most likely, you will also have some method of writing that data out somewhere where you can use it for audit purposes or retraining or comparison purposes. So there's generally an analytical storage layer as well. This implementation will end up being like a directed graph where you have everything kind of flowing in a somewhat of a synchronous manner. In the offline training and online inference, so the lower architecture diagram, you have your data sources coming in, and then you have this like bifurcation where in the lower part of the diagram you have a batch ingestion into an analytical storage layer like a BigQuery or Snowflake or something like that. And then there's the more common process we're all familiar with, or data scientists, machine learning engineers are familiar with, where you'll train that, you'll retrieve that data and you'll process it, and then you'll train a model or models, and then the most capable model will then be promoted into production. On the top side of this, top part of this diagram, we have what is could be referred to as a feature pipeline. So essentially, we have this tricky bit of this implementation, and for those of you who are familiar with like a Lambda architecture, or it is something like that, where you have to. The tricky part is that what you did to the data before you could train that model in that offline approach. You have to do the same thing to the data in a real-time fashion. And so you generally use a stream processing system here to extract the features in real time and then put them into a low latency storage layer. So in this offline and online mix, you have the model promoted to the serving layer, and you have the low latency storage layer where you have your features stored. And then the serving layer can query that low latency storage layer when it needs to retrieve features for the inference. And so you have this sort of mix of synchronous, asynchronous going on here. It's easier to implement, and there are like a wider breadth of models that can be used in this architecture. But I think that it's also harder to manage because you have that duplication of code, similar to what you would have in a Lambda architecture. So let's dive into this. But before we do, I wanted to call out two things, which will lead on to what we'll talk about next when we look at each part of the architecture. So the feature pipeline, or the stream processing pipeline that you have in the offline training and online inference, is, if we zoom out a little bit and ignore the inference now, is similar in that you have like a streaming input, processing, and then output, and then inference. And this is sort of the end-to-end latency of your system with respect to how your model can make inferences, is determined by the latency of this part of the system. So you generally need to, if you want to fit inside of real-time requirements, you'll need to do whatever you can to make this as low latent as possible. This might not matter in some use cases, but in some cases it definitely does. So the stream processing layer is generally made up of two parts. You have a streaming platform, and that's where you can have multiple streaming data sources. So this is most likely, it should be a system like Kafka or Red Panda or Pulsar, or there are some others. But the requirement of these sort of system, or like Kinesis or PubSub, if you're like talking about the cloud, the requirement for these streaming platforms is that they are, you can use the data in a streaming fashion. There's a low additional latency added, but they also are durable and replayable, to avoid data loss and to be able to replay that data in case you have a change in the downstream system and you have to do something like what is referred to as time travel, where you recompute the data out of that in the correct order for whatever purpose you need downstream. Downstream of the streaming platform, you have a stream processing layer. And this is normally where I would plug in Bytewax. You could use Bytewax to do that. But anyway, the stream processing, we'll talk about that more in a second, but the stream processing layer should be a stateful stream processor. What you're doing in the stream processing layer is you're either doing just some data processing for the feature extraction, in which case you most likely need to have an idea of what has happened historically, or you need to join data sources together on a key. And in order to do that, you need a stateful stream processor. That's why Bytewax, Flink, or Spark are usually used for this sort of this part of the system, because they can maintain in memory what has happened in history. So you can do modify the data based on the distribution over a window. After the stream processing is included in the system, we can look at the next part of the system, which is either going to be which will be your low latency storage layer and your analytical storage layer. I've referred to these as online storage and offline storage here, and you've probably heard that terminology before if you've been using a feature store. What the gist of this is that the online storage is called online because it needs to be readily available, and the offline storage is something that is cheaper storage and easily queryable in an analytical capacity. So offline storage, you'll generally have things like BigQuery or Snowflake or Parquet files in S3. And online storage, most commonly you'll have things like Cassandra, DynamoDB, Redis, or other systems where you can retrieve the data quickly based on like a key. Because what's coming out of the stream processor in the feature pipeline is basically features on a key with a timestamp, and then the downstream system will be able to retrieve those as required. Before we move on, I'll just talk about one more thing. In some instances, as we all know, like systems grow sort of organically at times, and it's not always as straightforward as the architecture diagrams I outlined. And in some cases, you have disparate data sets that are spread over multiple different systems, and you'll have to materialize those features into the online storage. So there, in some instances, you will compute your features on some cadence in the offline storage and then materialize them as required in the online storage. So I'll take a little brief aside here and talk about feature stores because they touch on what we just talked about. When feature stores as a concept came out into industry a couple of years ago, it was a little bit confusing of what exactly they were, probably because of the name store included store, but like it was what exactly was a feature store? We weren't really sure. Was it a database? Was it a pipeline? What exactly was it? The industry and all of us as a whole have come to some agreement on to what the definition of a feature store is. I like to define a feature store as an abstraction layer that unifies the storage layers and the materialization happening between them. So that's an interface into the streaming storage, the streaming materialization, the offline storage, and the online storage, and the materialization between those two. These are just 4 on this screen here. They're just 5 logos for different feature stores. You have Feast, which is contributed pretty heavily by the Tecton group, although Feast and Tecton are not the same feature store. Feast is open source, and Tecton is a closed source, and it's largely Spark-based. Then you have Hopsworks, which is this little hops thing here by Logical Clocks. Next to that, you have Vertex. Vertex is Google's feature store, and the other clouds have one too. There's a SageMaker and Azure have one as well. And then you have Featureform. Featureform I'm not that familiar with. But in essence, the parts of the system we talked about before, where we have the stream processing going on to do feature extraction, and then we have the materialization of data from the offline and online, and we have that retrieval going on. So your feature store is that interface into that. And if you've set up or worked with a feature store before, you might not even need to know what's happening underneath the hood. You can just they have like a nice API around most of these systems. And in some cases, they will host the system for you, the underlying storage, etc. So the final part of our architecture, which we showed earlier, is the serving layer. And this is different for the different architectures. In an online, purely online system, the stream processor is where the inference will happen. And in a offline-online mix, you'll have a separate model serving layer. So this could be as simple as like a Flask API or Fast API. It's available maybe as an endpoint, and then the client can request an inference from that, and at that time, that serving layer will pull the correct features from the online storage, and then you can make the inference. Generally, you should have some fallback for the features at request time, because most likely these model serving layer is in the request path of the application. So you do not want to have a breakdown in the system here, and at the very least you should return some naive response or use some default set of features. So you can kind of think of that online storage almost as like a feature cache mechanism, where you're retrieving the most or the nearest to real time, or the closest to the correct representation, and if not, you have a fallback. So that's it. That's all I wanted to talk about today. At the very end here, I'll just plug in something that someone made in the Bytewax community around real-time MLOps that goes into deeper detail. This GitHub link here that you can see here is an implementation that uses Bytewax, Feast, and I think it's Redis to build out the architecture that we showed before. So it's worth checking out if this is something you're interested in or something you're working on today. And then I'll also plug in Bytewax here. If you're working on a machine learning system, like what we've shown here, a real-time system, Bytewax is a nice project to use because it makes it easier to take the code which you wrote to do your training in the offline-online mix, take that same code and use it in an online fashion for the feature store. So whatever NumPy or Pandas based transformations you did in for training, you can then implement the same thing in a streaming context. And if you want to check out Bytewax on GitHub and give us a star, that would be awesome. I'll stop. Sorry, go ahead.
Yeah, no worries. Just turn down the microphone so that probably echoed. Yeah. Cool. Thank you, Zander. Let's give an applause. Thanks. You were so modest about Bytewax, so I will give some uppraise because we recently tried it and it's very efficient, very fast. We compared it to some Java-based technologies, and Bytewax, on the other hand, is based on Rust and has a very nice to use Python interface, which really sets it apart from the competitors. So that was a great experience.
Thanks.
Thanks. We have some questions here. Let me take the microphone. Oh yeah, we'll get Zander visit. Nice to see you as well.
Thank you for the talk. I was wondering whether you could give any use cases or general applications of this type of ML structures, because I felt like I don't really know when you would use something like this.
Yeah, that's a good point. For real-time systems, so I have one good example that I can give that contrasts batch system versus a real-time system, and it's from my experience at GitHub. So if you all are familiar with GitHub, there's the Explore page, and on the Explore page, there's a trending developers and trending repositories. And that was a system that I worked on, or the team worked on at GitHub, and it was a batch system where essentially we would compute for every combination of user and repository on the platform, what would be the best 20 or so repos and developers to show them, and then they would show up. So that's one system that is a batch system that we could have done in real time. So we had the data available in real time, but we decided not to. And the reason is that only 40,000 or so people ever viewed the Explore page and then went to the trending repo and trending developers. And after doing that, they never went on to purchase anything on the platform, or it didn't really change their experience on the platform. And so the decision to do it in batch was because we didn't have the expertise to do it in real time, or the available skill sets, and the ROI on learning all of the nuances around building a streaming based system was not going to be there for us. In contrast to that, there's just to try and use like a real use case to try and show why this real time might be used. Another thing on GitHub is stars, and like I'll ask you to go star Bytewax repository. Star spam is a real thing on GitHub. So people pay for stars because you can get funding or you can promote your project when you get a lot of stars. This affects the experience, the user experience on the platform, and really will to a detriment of the health of the platform if there are a lot of star spam users. So we tried to, we built a system so that we could shadow ban people who were star spamming in real time. So we used a combination of rules and machine learning implemented in real time with Flink on top of Kafka in order to shadow ban these people. And that was because there was a big effect and measurable effect on the platform if there was a lot of star spam. So it was one of those instances where taking on that complexity of the real-time system was worth it because the ROI was high. So in any instance where you have a trade-off between or any instance where you can get more value from data and a higher ROI as you move to real time, especially with machine learning, is an instance where you could use real-time machine learning.
Great, thank you a lot.
Yes, Mikko Kotola from Kempower. Maybe a question to Zander, that you're working on one piece in the very complicated ML and data engineering landscape, and we also saw some examples in the previous presentation. How would you compare it to these, let's say, more wider or bigger platforms? Maybe Databricks as a prime example. How would you describe? How do you see your piece and sort of building a platform for these pieces compared to using a more integrated platform for like as a data platform?
Yeah, so as a business owner and open source creator, we had to focus on you have to focus on and nail one thing before you can move on to a platform. So that's why Bytewax is so focused on one area. But I think more to your question, which is why would a user use a single best of breed in comparison to an entire platform? I think there's some nuance to that answer. If you're already using a platform, it makes sense to continue to use that platform rather than divest and invest in something else. What we see with Bytewax is there are a number of users, like developers, data engineers at smaller companies, and they have this like auxiliary or tertiary workload where you need to work with streaming data, or you need something to happen in real time. And that's a good instance. And maybe the rest of your architecture doesn't support real time, and that's a good instance. And when you might elect to use a single tool like Bytewax as opposed to adopting an entire platform. So I think it really comes down to a little bit to the use case and a little bit to like the organization and what they've already invested in.
Thanks. Maybe one more question is, like you show this architecture, it's quite can appear quite complex, or at least have many moving parts. So what advice would you give to somebody who is moving from batch and static data into the world of real-time data?
Yeah, I am doing a talk on this at a conference next week. My advice is always don't do it unless you can actually get more value for the business. If everything is already built in batch and you can do it in batch, like you should really ask all the stakeholders and really determine whether there's an actual value add before you take on moving your entire infrastructure required to support real-time use case. Because if you think about it, if most of your data is already in a batch system, you have to, every piece of data that you need will most likely need to move to a streaming system. So there's a lot of work entailed up the whole software stack to make it happen. So that's normally my answer is push back until you know that there's an actual value added there for the business.
Great advice.
I wish I could see better what's going on